I've noticed something odd happening on Getaway lately. When the ball goes around the orbit shot in the back of the playfield, there's a sound that plays, and the lights in the playfield really briefly go dim. It sounds a lot like the sound that plays when the ball is going around the supercharger. And that same dimming of the playfield lights happens at that point in the supercharger. So I suspect that I've got a problem in the switch matrix, where the machine thinks there's a ball in the supercharger, when really the ball is in the orbit. I'm trying to dig into why that's happening.
Let's take a look at some gameplay to figure out what is triggering the problem. It seems to happen when the ball is in the orbit shot around the back of the playfield. A typical orbit shot is supposed to look and sound like this. But in this next orbit shot, you can see the lights dim twice, and hear additional engine sounds being played as the ball goes around.
It happened multiple times during the same game, and it happens pretty consistently, but only in one particular orbit shot. The ball can enter the orbit a few different ways. The launch, the left orbit, the loop shot, which is pretty much the same as the launch shot, and a right orbit. The ball crosses all of the same switches, regardless of which way it enters, from the right or from the left. But the issue only occurs if it enters from the left. It doesn't happen when the ball enters from the right, and it doesn't happen when the ball goes through the loop.
There are 4 switches in the orbit that the ball activates when it rolls through, 2 on the left and 2 on the right. The machine uses these 4 switches to determine when the ball is entering the orbit and which direction it's going. There must be something going on with these switches.
We can use the machine's built-in diagnostics to help figure out what the problem is. Specifically the switch tests. The machine has a bunch of built-in diagnostics and tests. There are 3 switch tests that are going to be useful in this case. Switch edges, which tells you the last switch that was closed, and switch levels, which tells you all of the switches that are currently closed. It cycles through each of them. And single switch, which allows you to sit on one particular switch and see the state of that one switch. So let's go to switch levels and take a look at the switches at the back of the orbit. So you can see on the display that the machine is cycling through several different switches. So this matrix, this array of switches, shows all of the switches in the machine. There can be up to 64 different switches. And the ones that have the green box around them are the switches that are currently closed. So if it was a micro switch, it would be down, the switch is closed. The 3 right here, you can see as the machine cycles through them what their names are: left trough, center trough, and right trough, are the 3 switches where the balls are sitting, where the 3 pinballs are sitting. So those balls are sitting on top of switches and holding them closed, and that's why they appear to be closed. All the switches here are the optical switches on the supercharger. So you can see when I break one of those optical beams that the switch isn't closed anymore. So when the beam is unbroken, the infrared is going across, the switch is closed. If I break that beam with my finger, the switch is open, and the green box is no longer around that switch. There are several switches like that around the supercharger, and that's how the game tracks where the ball is around the supercharger. There's another one right here at the entrance that I can close with my finger. There, and you can see when I break that switch with my finger, it's no longer closed. So all of the switches that are closed right now are the ones we expect to be closed, including this one straggler over here, which you can see the machine just said is always closed. On this machine, that switch is always closed, and it's just a consistent switch that you can use to know if the machine is correctly reporting the switch states, because you know that one should always be closed no matter what. So you can see if I manually trigger one of the 4 switches at the back of the orbit. There's 2 over here, and there's 2 over here. I can manually trigger that switch, and we'll see it closes. So open, closed, open, closed, and it's the right freeway is the switch that the machine said it is. I can do the same over here if I can find it for the left side. Open, closed, open, closed. And that's the left freeway bottom. So those switches seem to be working just fine. Now there's 4 switches back there. I can only really reach 2 of them. The other 2 are farther back, and I have to take the whole supercharger ramp off to get to those. But luckily I was able to spot the problem without taking the supercharger ramp off. Let me go to a different switch test, and we'll take a look at what I think the issue is. So we'll get out of this switch levels test and go into the single switch test. So the one I want to take a look at first is the left freeway bottom switch. So that's this one here. You can see if I manually close that switch, the machine reports the state as being open or closed. Now that switch seems to be working just fine, and this switch over here was working fine as well. You can see it's being reported. The machine just isn't telling me because I'm only querying a single switch right now. So no issues with those switches. I don't see from this test any reason that the machine will be doing what it's doing with dimming the lights and playing the extra sound effects, because those switches seem to be registering just fine. But one thing I noticed is it only happens when the ball is going around, entering the left side, so on a left orbit. And what's unique about my left orbit on this machine is I've got a mod in place, and it's this spinner. This spinner is actually attached to the switch over here, the switch 15. So you can see when I spin it, it's closing that switch 15. If I hold it up like this, it stays closed. So this is like an extra switch that's just piggybacked on top of this switch over here. Now, one interesting thing is if I hit the spinner really hard, this can spin for a while. So it's opening and closing, opening and closing, opening and closing. And sometimes it actually gets stuck in a state like this, where it's being held closed, just like this. And what I found is, while this is closed, if I manually trigger one of these orbit switches over here, not only does the orbit switch trigger, so I'm holding it closed right now, but you can see one of those optos opened, as if there was a ball there, breaking that beam. So let's adjust the switch test to go over there and put a watch on just that switch. So it's the opto-made loop switch. That's this one right here, the supercharger. That's the switch on the supercharger that signals to the machine that the ball has made a complete loop of the supercharger. And during gameplay, when the ball's going around the supercharger, this is the switch that signals the machine to play the supercharger sound and to dim the lights in the playfield. So the fact that that switch is being incorrectly triggered when this switch is closed and one of the orbit switches gets triggered like this. See, that switch shouldn't be affected by this switch, but it is. That's what's causing the extra noise to be played when the ball is going around in orbit. And that's also why it seems to only get played when the ball enters from the left side. That's because this spinner may still be spinning when these switches back here get hit. So this is a classic switch matrix problem. On a pinball machine, the state of any one switch really shouldn't affect the state of any other switches. And just because the switch is held down, like if I hold down this switch here, you can see, there it is, other switches still work. Like that switch there still works, even though I'm holding down other switches. All the switches should operate independently. But in this one particular case, this switch is affecting other switches. So this is a switch matrix problem, and we have to take a look at the switch matrix to understand why this is occurring. Let's take a look under the playfield and see if we can figure out where the issue is. Now, switch matrix problems can be a little tricky. Almost always, if you've got an issue with a particular switch not behaving correctly, the problem isn't going to be with that exact switch. It's probably going to be with another switch on the playfield. And you can typically, with some knowledge of the switches in the particular game and what they're used for, you can most of the time narrow it down to a small selection of switches, maybe 4 or 6 switches that could be the issue. Most of the time it's not going to be the switch that is misbehaving, although you do have to look at that switch. And this is just the nature of the switch matrix. But in this case, I suspect that the switch that we're going to be having trouble with is the one that I've piggybacked the spinner onto. If anything, just because this machine used to work fine, and the issue didn't start happening until I added that additional spinner that I piggybacked a switch on. So I'm suspecting that maybe the issue is with this bottom orbit switch on the left, just because that's where my spinner is piggybacked on. You can see the red and black wire here. It goes from the spinner down to the switch. And if I take a look at the switch, yeah, okay, so I messed up. Let me bring you in closer and take a look at this. Alright, so the spinner comes down this wire here, and it is piggybacked onto this switch here. You can see the red and black wire goes to those switch contacts. And boy, it's hard to get a good view of that. But I can already see what the issue is. Now, to understand what's wrong with this, you've got to have some knowledge of pinball switch wiring and the switch matrix on pinball machines. It's going to take a little bit of theory.
A typical switch circuit might look something like this. There's a voltage source on the left, ground on the right, and switch in the middle. Before the switch, there's some sensing or processing circuitry used to tell when the switch is open and when it's closed. When the switch is open, there's no path to ground, and the processor sees positive voltage. Using this type of circuit, a processor can tell whether a switch is open or closed. When the switch is closed, there is a path to ground, so the processor sees very little voltage, basically ground. The circuitry in a pinball machine is far more complicated, but you can still basically conceptualize it like this. Today we think of pinball machines as novelty items, with maybe more owned by personal collectors than those found in arcades. But back in the day, these machines were almost exclusively operated in arcades. They were purely money-making devices. They were built on a budget to minimize the investment and maximize the profits. Pinball machines have an incredible amount of components, circuitry, and wiring, and they're built by hand. It takes a lot of material and manual labor to build a pinball machine. With so many components in a typical machine, pinball manufacturers had to look for ways to reduce circuitry and wiring to minimize labor and material cost. The different parts of the switch circuit are split up between the backbox and the playfield. The engineers designed the switch matrix in order to reduce circuitry in the backbox. A typical pinball machine has up to 64 switches. Instead of having 64 separate power, sensor, and ground circuits, the switch matrix allows the same circuitry to be reused across multiple switches. The switch matrix also minimizes the cabling between the playfield and the backbox. Without the switch matrix, each of those 64 switches would require 2 wires apiece between the playfield and the backbox. 1 wire for source voltage and 1 for return. The switch matrix supports all of those switches with only 1/8 of the wiring, reducing labor and material cost. The problem that I am having with Getaway is peculiar to the switch matrix. To understand the root of the problem, we have to understand the switch matrix. The actual switch matrix is pretty complicated. It's well above my understanding, to be honest. But we can simplify it a bit and build up to it, starting from this basic switch circuit. The goal of the switch matrix is to reduce circuitry and cabling. So let's try to reuse this power and sensing circuitry for a second switch. If we just tack on a second switch, now we have 2 switches using the same power source. That works, somewhat. The processor can detect when the first switch is closed, and it can detect when the second switch is closed, but it can't tell which switch is closed. When either of the switches is closed, the processor cannot tell whether switch 1 is closed, or switch 2 is closed, or both of the switches are closed. We can address this problem by having the processor control the grounds of the switches. If the processor grounds only one of the switches at a time, then it always knows which switch is grounded. When the processor is grounding switch 1, if the processor senses ground, then it knows that switch 1 is closed. When the processor is grounding switch 2, if the processor senses ground, then it knows switch 2 is closed. So now we can reuse power and sensing circuitry to support more than one switch. But in doing so, we have introduced more complicated ground circuitry. So let's take a look at how we can reuse that ground circuitry for more than one switch. Quite simply, we can just add a second set of switches that use those same processor-controlled grounds. The schematic is starting to get more complicated now. Sometimes when lines cross, they are connected, and sometimes they are not. If there is a dot where the lines cross, that represents a connection point. Those wires are connected. Where lines cross without a dot, there is no connection there. Those wires are not connected. So now we've got 4 switches using only 2 power circuits and 2 ground circuits. Let's take a look at how that works. The processor only checks one switch at a time. When it is checking switch 1-1, it grounds column 1 and checks row 1. If it senses ground, then it knows that switch 1-1 is closed. Similar when checking switch 2-1. The processor grounds column 2 and checks row 1. If it senses ground, then it knows switch 2-1 is closed. To check switch 1-2, the processor grounds column 1 and checks row 2. Here the switch is not closed, so it senses positive voltage. Finally, to check switch 2-2, the processor grounds column 2 and checks row 2. If it senses ground, then it knows switch 2-2 is closed. In the scenario we just walked through, 3 switches were closed and 1 was open. In that situation, if the processor was checking switch 1-2, then we would expect it to report the switch as open. Only column 1 is grounded, so there is no path to ground for switch 1-2, so the processor should see positive voltage. and report that the switch is open. But unfortunately, that is not what happens. In this situation, the 3 closed switches actually provide a path to ground. The current travels through switch 2-2, switch 2-1, and switch 1-1, and finds ground on column 1. Because of this, the processor will incorrectly report that switch 1-2 is closed, even though it is open. This is a big issue. Multiple switches get triggered simultaneously all the time in pinball. So how can we fix this problem? Well, we add diodes. Diodes only allow current to flow in one direction. Here in the diagram, current is only allowed to flow in the direction of the arrow in the diode symbol. Current can flow into the triangle and through the rectangle, but it cannot flow in the opposite direction. So in this situation, current will flow through switch 2-2, but it cannot flow past switch 2-1, so it cannot find a path to ground. This fixes the problem, and the processor correctly reports that switch 1-2 is open. So we end up with a small matrix of switches that looks like this. 4 switches in 2 rows and 2 columns, with diodes isolating them. Each of the switches share a voltage source and a ground with other switches. To simplify it a bit, each switch in the matrix looks like this. They have a row connection where they source voltage, and a column connection that the processor grounds to enable the switch. We have been working with 4 switches, but pinball machines typically have around 64 switches. To accommodate that, we just need to add more rows and more columns. 8 of each to be exact. 8 rows and 8 columns gives us 64 switches. This is how the switch matrix is constructed in most pinball machines. You can see evidence of this in the manual, where it shows the switches arranged in an 8x8 matrix, and also on the diagnostic display on the DMD. Each switch is numbered, with the first digit representing the column and the second number the row. And the switches that we have been looking at are displayed in an 8x8 matrix. So that explains why each switch that you see on a pinball machine has a diode attached to it. That diode is the root of the problem that I've got on Getaway. Let's take a look at this switch again, and we need a bit more theory to understand what's wrong here. The micro switch is wired like this. The original wiring is white and green for the row, and green and brown for the column. I added the red and black wires for the spinner modification. You might expect a switch would just have 2 contacts, but micro switches like this have 3. They're labeled NC, NO, and COM. Those stand for normally closed, normally open, and common. Pinball machines typically have a diode installed between the normally closed and common terminals. Internally, when the switch is not active, the common terminal is connected to the normally closed terminal. When the switch is active, the common terminal is connected to the normally open terminal. The diode is installed between the normally closed and common terminals, like this. The row and column wires are attached to the normally closed and normally open terminals. This seems like an odd way to wire a switch, and it did not make much sense to me until I drew a schematic for it and realized what happens when the switch is activated. When the switch is pressed, the common and normally open terminals are connected. So when current traverses from the row wire to the column wire, it has to flow through the diode. If you remember the basic switch circuit in the switch matrix, that is exactly what we want. When a switch is closed, power needs to flow from the row, through the diode, to the column. I have the spinner modification installed, so I've got a couple extra wires attached to this switch. They're connected to the normally open and common terminals, like this. When the switch is activated, power flows from the row to the column, through the diode. And when the switch is not active, no power flows between the row and column. But remember, the spinner is attached to this switch, and it has a switch of its own. When the spinner is not active, everything looks fine. But when the spinner is active, that's where the problem occurs. Power can flow from the row to the column, so the spinner switch works, but the diode is shorted. Current can flow right past the diode, which means it also can flow backward through the switch matrix. We saw why diodes are important in the switch matrix, and what could happen if they were not installed. Bypassing the diode in this situation has the same effect. Whenever the spinner switch is closed, and the original switch is open, the diode is shorted. This allows current to flow backward across the switch, and leads to switches being registered incorrectly. This is why the supercharger opto is activating when the spinner is active and a ball rolls through the orbit switches. If I remove the spinner entirely, I think the machine would work fine. But I like the spinner, so I have to figure out how to change the wiring to make it work. There are a few requirements. Both the original switch and the spinner have to work separately. The switch should register when the original switch activates and the spinner is inactive, and the switch should register when the spinner is active and the original switch is inactive. Both switches should work simultaneously, so the switch should register when both the spinner and the original switch are active. And finally, whenever the switch is active, the row and column have to connect through a diode. It's that last requirement that is causing the failure. Both switches work, but when the original switch is closed, current is bypassing the diode. I think the best way to accomplish all these things is to wire the spinner pretty much like the original switch. Add a diode on the spinner switch between the normally closed and common terminals, just like the original, and then piggyback the spinner on the original switch between the common and normally open terminals. Let's test the requirements and see if that will work. Both switches must work separately. Let's test the spinner first. If the original switch is inactive and the spinner is active, power is able to flow between the row and column. Good so far. Now let's test the original switch. If the original switch is active and the spinner is inactive, power is still able to flow between the row and column. So that requirement is satisfied. Now we have to make sure both switches can work simultaneously. If the original switch is active and the spinner is active, power is still able to flow between the row and column. In fact, the spinner is pretty much bypassed in this case, but that's fine so long as the switch registers. Now we need to make sure that no matter how the switch activates, current always flows through a diode. If the original switch is active, current flows through the original switch's diode, and the spinner circuitry is bypassed. Good so far. If the original switch is inactive and the spinner is active, current flows through the new diode on the spinner. Looks like this new wiring meets all the requirements. I think wiring the switch like this is going to solve the issue. So we have a plan. I want to wire a diode to this switch, which is covered up by this 3D printed gate. I've got to get the gate off, and it's screwed into the playfield underneath this large plastic. So I'll have to pull this off to get access to the micro switch and add the diode to here. There are two screws that secure the spinner to the playfield. To get to the screws, I need to loosen the metal habit trail in two different places and move it aside. Then I can unscrew the plastic and wiggle it out from underneath the habit trail. Now I can unscrew the spinner gate and get a look at that micro switch. I can confirm now that there is no diode on this switch. And that's what we're going to have to add to fix this switch matrix problem. The two wires for the spinner switch go through a small hole that I drilled in the playfield. I want to remove the spinner from the machine entirely so that I can get better access to add that diode. The spinner wires are soldered to the original switch under the playfield, so I need to unsolder them to be able to remove the switch. So I unscrew the switch from the playfield to get some more room. Then I can unsolder each of the two spinner wires from the switch, and I can feed the wires back through the hole in the playfield. The spinner microswitch is held to the gate with two small machine screws. After unscrewing those, the microswitch comes right off. The wires were originally soldered to the common and normally open terminals. That would be correct in typical non-pinball usage of this type of switch, but we need to be connected across the normally closed and normally open terminals. So I unsolder the wires from the switch. That gives me more room to add the diode across the common and normally closed terminals. I use a 1N4001 diode, which is commonly used for pinball switches. Then I solder the wires on the normally closed and normally open terminals, making sure to keep everything nice and tidy so that it fits within the gate housing. I reattach the switch to the housing using the 2 screws, and then make sure that the spinner still activates the switch correctly. To test the wiring, I put my multimeter in diode mode and measure across the wires. When the switch is open, there should be no connection between the 2 wires. When the switch is closed, we should be measuring across the diode, so the meter should show about a half-volt difference. Looks like we're good to go. Reinstallation is the reverse. I feed the wires through, install the gate, install the plastic, and secure the habit rail. I solder the spinner wires to the common and normally open terminals of the original switch, being careful to get the orientation correct so the diode functions in circuit.
So hopefully that's it, and we'll lower the playfield and give it a try. So we're back in the switch I just tested. At this point the spinner should work, and it does. Hopefully the original switch works too, that the spinner is connected to, and it does. I guess I want to make sure there's no odd behavior when the spinner is closed and the switch is closed. And there's not. Everything's fine. The original problem was that when this switch was closed and I hit this switch back here, it caused the opto to open. That's not happening anymore. You can see when I push this switch here, the only thing it affects is that switch. I guess for good measure, I should make sure the opto still works. It does. So it used to be when I hit this switch back here, it would close this or open this opto, just like it does when I put my finger on it. That's not happening anymore. So it looks like everything's solved. The switch matrix is back to normal, and this shows what effect a single diode can have on the switch matrix. You can see how, and this was actually a pretty easy problem, you can see how just one diode being bad somewhere can cause some really odd behavior in a pinball machine. I remember when I first got my pinball machine, my very first one, I was doing research on different problems that you can have with them and the maintenance, and I ran across discussion of a switch matrix issue, and I thought, oh, that's crazy. I don't know if I'll ever be able to diagnose that. I hope I never have any problems with the switch matrix like that. But it's really not that bad. With just a little bit of knowledge of how it works and the theory behind it, you can tackle switch matrix problems. This is the second one I've had, and I've solved both of them. So a little bit of knowledge of theory, a little bit of knowledge of how it's constructed, and switch matrix is not a problem.